this graph is showing the water level of Lake Victoria from the historical water level of Lake Victoria and the highest that we felt in 2021. So we have the minimum, the average water level from 1900 to 1960. That is indicated in green. The red line is the long-term average from 1900 to 2021, and then the black line is the long-term, the mean lake level average in the period from 1963 to 2020. Lake Geauga, from our investigation, the highest water level was recorded on 18th December 2020, and then the lowest water, and for that is a comparison. Sorry, this is a graph that is comparing Lake Geauga, Lake Albert, and Victoria water level for the period of 2020 and 2020 to 2022. Yeah, for that period. And the red line is showing the highest water level recorded for Lake Geauga. The black line is showing the highest water level recorded for Lake Albert on 18th December 2020. And the blue line is showing the highest water level recorded for Lake Victoria on 14th May 2021. The 2020-2021 flood extent for Lake Geauga, we can see the map that shows the red line, the red dots you're seeing is for 2020 extent, and the blue line is 2021 extent. And this to the right is a picture showing the extent of the damage that it caused for this period for Lake Geauga. And for Lake Albert, we have the extent. The red one is showing the extent for 2020, and the blue line is showing the extent for 2021 for Lake Albert. So for the full finding, the impact of the rising water level for Lake Geauga, we found that in one sub-county, that is Wampanga, over 3,000 people affected. That is in Nakasongola district. In just one sub-county, that is Wampanga. People are from Chikonjiro, the Wampanga sub-county. A lot of people that were displaced were taking shelters in churches, in mosques, schools, and under trees, at friends' home. And this graph just shows in the sub-counties or in Geauga where the impact is high. And one of the major structures that were affected were the docking pier at of MV Geauga at Zengabia landing site. And then we have hospitals affected. We have police posts affected. Over 1,000 households affected in Kalashi district, but also more than 200 acres of farmland. That is just in one district. And this is the survey just done in one district. So for the destruction that is estimated by the climate knowledge, it estimates the destruction for the 2020 flood to $62 billion in GDP for Uganda. The impact of the floods for Albert. Now, for Albert, we had, sorry, this is still for just a picture that is showing for the impact for Geauga on the infrastructures that have been affected, how people are taking shelter, the water sources, the road. So the impact, this is us actually moving on a road that was submerged, and it was part of a lake, using a boat to go through to the next sub-county. For Lake Albert, over 500,000 people affected, including sub-county, including landing sites, hospitals, and roads. And also this intensified with landslide that happened within the region. So this is just a compounding impact of the 2020 and 2021 water levels. So what are the levels throughout the management of the floods? What lesson did we learn as a ministry and as an agency that is responsible for flood management? One of the things that the lesson that we learned is that there is need to define roles of various institutions in flood management. We often realize that most of the management issues that we had to deal with was there's no proper channel of communication. Even when you communicate, the communication reaches the top management, but little or nothing is done. So there's need to define proper role of each institution in the flood management and how to respond when a flood occurs. Then we also realize that the departmental capacity to forecast floods is still limited. While we knew that the flood was going to happen, we did absolutely nothing. So we did not do any action to prepare the community. Even the top management did know that it was going to flood, Lake Victoria was going to flood, but nothing was done in terms of preparation to the community, in terms of forecast, the forecasted flooding event being financed to trigger preparation for the local community to understand what is to come. And also the regional cooperation and data sharing. So we noticed that the mechanism of data sharing is quite it's not there. We still do not share data among ourselves, between institutions, between departments, and between countries as well. So that in a way also hindered the response to the flooding, but also we realize that it's the community that is often affected other than us who sit and do the management. Also, the access to funding. So funding is a big thing. Normally when we talk about funding, it is more of who can bring money and to pay an activity, but funding to just do with the preparation, making resilient structures to make sure that when a flood happens, structures are up to date and they can withstand the flood. A case is all the landing sites, all the docking site along the Nile and on Lake Albert and Chioga, all of them could not withstand the flood that happened, and most of the docking places had to be stopped. The ferries had to stop moving. So there's also technical and technological gaps within institutions. So we need to, I think, build more capacity of the in-house staff in terms of technology available in the market, and we use it to better understand flood and the emergency that it caused. And also what we know, we've learned now is that we respond after a flooding event happened. How about we start with early preparation when a forecast is made, and we are absolutely sure, like we were sure for Lake Victoria, to respond, to start with assessing the structures that could be affected, having disseminating information to the community for better preparation. Just do a bit of preparation for the community to understand what exactly at stake and how they can manage the coming disaster. So the impact of COVID-19 did not leave us, because it happened at the time when COVID-19 had just started. Everyone was on lockdown, and that in itself also hindered our response as a ministry to go for action and also assess the impact, but also try to respond to the community that was affected. So one of the things that we also notice is that there is little or no enforcement of the existing laws on the buffer zones of the different lakes and wetlands and rivers. So that in its case also it made the flooding problem worse than it should be, that those who are living in the buffer zone could have left before the event had happened, when the early warning was made. And also the economic status of the community, we realized that even if we had also notified them, some of them didn't have where to go exactly, so they would still stay. But again, we would say the impact would be low as compared to what has transpired for the past for that period. So in conclusion, we recommend urgent need for flood forecasting unit to be operationalized with the Ministry of Water and Environment and the Monitoring and Assessment Department. We already have a structure that is capable enough. We just need to operationalize it. There's also need for proper and timely channel for communication for early warning to be established, and flood victims should be compensated. Also, establishing of more monitoring stations and flood management strategies for timely response should be put in place, and the impact of the floods on Lake Kyoga and Albert are devastating and requires a holistic approach, and flood control measures downstream of the Nile should be implemented. Yeah, so since Lake Kyoga is very shallow, it literally got the greatest impact because all the water that was coming from Lake Victoria was dumping itself on Lake Kyoga, and therefore the extent of the flooding was much greater, and a lot of people were affected, a lot of housing, a lot of infrastructures that up to now the community is still trying to cope up with what has happened and come back to normal. So there is need to put more emphasis on the flood management downstream of Lake Victoria, to see that the management strategies that are being done on Lake Victoria also copied or done on the other downstream lakes like Lake Kyoga. Thank you very much. This makes the end of my presentation. I want to thank NBI for this opportunity, but also thank the AKR Center for Aquatic Research and Education for allowing me to do this research. Thank you.
Thank you very much for your very nice presentation, Ms. Pasca. Now we directly go to the next presenter. Before that, participants, please type your question in the answer in the A. Also, presenters, please check by going to Q&A questions for you and try to answer in Q&A also. The next presenter is Professor Yilma Sleshi from Intro, Ethiopia. Professor Yilma is a practicing hydrologist or water resource engineer with experience in dam hydrology, flood, spillway sizing, reservoir operation, road drainage, and water resources system modeling. Presently, an associate professor in hydrology at Addis Ababa University. Yilma's background is in civil engineering with postgraduate study in hydrology and PhD in applied science. His dissertation is in stochastic prediction of seasonal rainfall in Northeast Africa and India. His specialties includes hydrology, seasonal rainfall prediction, reservoir operation study, drainage study, and the water resource system. Professor Yilma's presentation is on Eastern Nile flood forecast and early warning system enhancement. Dr. Irma, the floor is yours. You can go ahead and present your presentation. Thank you.
Thank you, Zallaka. And thanks also for this excellent coordination of the webinar. So my presentation will be on the Eastern Nile flood forecast and early warning system enhancement. It has 4 components. The first one is about major flood years experienced in Eastern Nile and some impacts. On the second will be on flood forecasting and early warning from the beginning 2001 to 2023 in Eastern Nile countries. The current enhancement work at intro and challenge and improvement areas in flood forecasting and early warning system. I hope you see some of the letters are a little bit smaller to keep all in one. This is recent, actually. Historically, flood has been there from time immemorial. 1878, 1946. This was the most devastating flood in Blue Nile, and 1988 was also much known, both Blue Nile flood and direct rainfall in Khartoum, causing major damage. Then notable one were 1996 and 1998 flood. This is still in Blue Nile and also in Gambela. Then in 2003 in Sudan, it affected more than 150,000 hectares of irrigated crops and many damage, displaced many people. If you see this chart, you will notice that although the frequency looks much closer in years, but this is in fact the way we recorded it. Flood is a common phenomenon in Eastern Nile. The damage is also enormous. In my literature survey, I noticed that, and also from my visit in South Sudan, recently, 2021 and 2022, there were a lot of inundation in South Sudan, and this coincided, as my friend Ajok explained earlier, with the rise of Lake Victoria. So more rain in the equatorial lake area, resulting in high water level in Lake Victoria, so more releases. Then you see, compared to 2013, a large area was flooded in South Sudan. So directly the Lake Victoria has impact in South Sudan flooding. Now, flood forecasting and early warning system, it is not a modeling aspect only. I will go this WMO guideline little bit slowly. For modelers, maybe we focus on flood forecasting early warning systems here about the data itself, whether we have experts to do that, and the proper software. Well, to do that, behind, of course, hydrological data, meteorological, topographic, and social infrastructure data is required. But the most difficult task comes in particular in Eastern Nile and in many developing countries, is to have a measurement of discharge and rainfall well distributed at right locations. So even we have that, transmission of this data in short period of time, in quality checked, to the modeling center is still a major challenge. So when we model, water level or discharge amount at one location, the product will be the flood warning. So what the effective flood warning include? For that to happen, a warning should come single authoritative voice. It's not from various authorities. When the flood will occur and reach certain height. So this is to some extent, although you have years of certainty, you will act in as you go on, and the areas that may be inundated. So you have to be specific, and you need also to tell the depth of water. Is it at the knee or above that? And other factors which may affect safety depending which community or which infrastructure you protect, your warning system should address. Then, who are the potential users? So, sure, the first to hear is the high-level government decision makers. They are the ones to decide the warning. And then the private and public infrastructure managers, they also need this information. They may receive this directly. And the emergency services also need disaster risk management officers. They need all of the service. And of course, the one who are affected at the ground, the communities should receive these services. So they are the potential users. This in a very modern urban area, this for may be the case, but in Eastern Line setting, the community should also receive this information. Now, the flood warning, what we give when we make our modeling exercise, we need to think of what exact information we are giving them so that the emergency personnel prepare themselves very well to protect the flood affected areas, alerting people about the flood timing and location so they can prepare. All these coordination aspect has to come closely. So the possible responses, depending whether you are rural or urban areas, may vary. Now, often the response is coming from Disaster Risk Management Commission and Ministry of Defense and other bodies. So a major coordination is required. Pre-planning and preparation has to be done. And finally, of course, the way you transmit that to the local community and all these hierarchies, what I mentioned, it is a very delicate path. It has to be a stable path. During even flood time, the message has to reach. You have to design this carefully. So it's not only modeling, the modeling aspect here, but all this has to come if we have to produce a robust flood forecasting and early warning system. Now, in Eastern Nile, we have been trying to establish this flood forecasting system since 2001. So the first things, this is among countries. So the institution has to be set. So this is an important step. Intro was established at that time. So the ministers there, the 4 countries, or the 3 countries water minister at that time decided flood is a major issue for their country. So they want to establish the flood forecasting early warning systems. This is an important step. So the first project at that time was on flood preparedness and warning. Then to do this, one has to connect to each country's flood forecasting center. So establishing the flood forecasting center at the four countries, now South Sudan is included, become then critical. So that decision also was made. Once the centers are there, then the extent of the modeling has been already prepared by earlier project. The SMEC did this work. Then the institutional, the cooperation, the technical aspect proceeded. So from the higher level, it goes to the technical, basically to the technical level. And in that period, up to 2010, piloting of flood preparedness emergency work has been done in Khartoum, Tuti Island area, in Ruman, and in Lake Tana areas. Now, recently, through NCORE project, the complication of flood forecasting early warning is known, but sustaining that product is very important. So there was an attempt to strengthen the flood forecasting system and expand to unmodeled area at Lake Atbara and Bas in Gambella and the Sobat areas. So now we are coming in the current project under NCCR. We remember we built it is now already 10 years already passed. More than from the very beginning, more than nearly 20 years. Then we try to consolidate the modeling exercise by conducting additional topographic and infrastructure and socioeconomic survey. This work is now being finalized. It's a very expensive task. Topography, all what we're talking about, topographic means the vertical accuracy we look is more than 1 meter. Actually, desirable is 0.5 meter. And the horizontal resolution, not more than 5 meters. Buildings known, infrastructures, roads known, but with their quality and also associated economic value. If they are attacked by water, by how much is the loss? All this has to be done correctly, and the socioeconomic impact due to flood for that flood-prone area has to be also captured well. So it's an expensive, time-taking effort. So for some selected flood-prone area, we did this one, and now currently it's already in this Sunday. The inception workshop will start on enhancement of Eastern Nile flood forecasting and warning system. So this is model enhancement with better data of topography and infrastructure, and also with recent findings of rainfall forecasting. If they are helpful, we're going to improve the modeling. And also there is another focus now on community to make them more aware about flood. Of course, we know they are aware, but awareness in terms of preparedness and or maybe improve some of their perception regarding flood. So if you go a little bit deeper into this modeling activity, which might be for researchers, this is maybe very useful. Now, what we do at Intro, anywhere also in who's modeling flood forecasting and warning system, the driver is rainfall. No rain, no flood, so things stop there. What we do at Intro, we use WRF model. This is a general circulation model prediction. So we make forecasts through this. So improvement in this will dramatically improve what is going down. Now, the second part, this is on forecast mode. The second part we need to continuously improve the forecast based on observed rainfall. So the observed rainfall now it is getting closer to ground observation. So this rainfall estimate based from satellite data will be used, in fact, to calibrate the rainfall forecast. Behind the calibration factors will come in forward forecasting, but a continuous calibration can be handled by this satellite rainfall. Then the hydrology model, we take in the forecast rainfall 3 days ahead, 1 hour time stay forecast rainfall. We are using NAM model, and then produce hydrograph. Then this hydrograph then goes to the hydraulic model to Mach 11. So for Mach 11 to work properly, we need to have a very sound cross-section, river slope, Manning coefficient, and the floodplain characteristics. This is the most difficult, it's because, we are dealing with 1,000-kilometer stretch, damn expensive for all to be, very accurate. So we have to then select only the flood-prone areas. The other, we model it a little bit in a rough way. Now, this input in forecast mode, this will go for early warning system. But you can also use this to assess the flood hazard, the flood exposure, and the flood vulnerability, which the multiplication of this, as you know, help to produce you the flood risk. So actually, for people to evacuate, you have to tell them the flood risk. The hazard, you can't tell them the extent, the depth of water, but it has a meaningful to them if you tell them the flood risk they will encounter. The same modeling approach, rather than rainfall forecast taken out, using historical rainfall with probabilistic method, you can also assess the flood risk for a given flood plain. Now, in hindcast, this rainfall estimate which I mentioned earlier. So continuous calibration it's required. So the model should be able, your flood forecasting and rolling system should be able to accommodate this internally to calibrate your forecasted rainfall for that year, because when you forecast August, you have the July estimate. Of course, the July calibration might be, the July calibration may work for July rainfall, the August may be for August, but still, if it improves the forecast, one can use that one. Now, recently in 2021, many of you might have encountered this report, this paper, assessment of precipitation error propagation in discharge simulation. So the error you have in rainfall forecast, how much is reflected in discharge? And of course, how much is reflected in risk is another story. So they said it's linearly propagate. Linear, of course, it has some coefficient depending on the situation, but it's not exponential what they discovered. This is one research. Another research may show differently. For error will propagate, but by how much it propagates is another issue. Knowing this is also important. On a WRF, in a recent paper in 2022 by Highlight, he found that for 1 day to 3 day lead time forecast, reasonably reproduce the observed data. The low rainfall and high, greater than 60 millimeter day, well modeled. But he said from 6 to 60 millimeter, the correlation is low. This is his finding. So the research has to go on by making a longer period of WRF calibration, where it is strong and what is the factor to modify this value. Now on hydrology aspect, still we know, we estimate flood hydrograph. and peak discharge itself, and depth of water and the extent of flooding using the hydraulics. But we are not sure of what is the major factor of uncertainty. Is it manning roughness, or is it the change in the rainfall itself, what I discussed? Where is the source of answer? It's not known. Maybe vary from catchment to catchment. But for a specific flood-prone area, one has to look for this. For risk management, also the same way. What is a greater source of uncertainty? Knowing this will help you to focus in improving. The challenge we have recently, many challenges we have passed. Still, observed flood hydrographs and corresponding aerial rainfall, observed one. We have few stations and data exchange problem is there. The accuracy of rainfall forecast is also still a challenge. Rating curves have not been updated, if we have, and the resolution which I mentioned earlier, and also accurate asset map and infrastructure maps with property values. Their exposure and vulnerability especially is not well quantified. So for flood risk assessment and to give value for our forecast, this has to be really acquired in the right time. The institutional capacity building is also an issue. Concise and relevant definition of early warning content, format, and channel still we lack this. The content for stakeholder, for decision maker, and the content for the community is, the way they want is different, but this should be basically more or less one content across when you pass the message. Because the media, we say something, but on paper, if something goes, that will be difficult. Well-established sustainable institution and their chain from forecast generation and emergency decision generation up to the flood affected community is not there in Eastern Nile. So it's a lot of work has to be done. Sustained action on flood mitigation, preparedness, and emergency response. This is also not well taken by the national governments. So it is recommended to conduct, now looking all these issues, to conduct ensembles of forecast of flood and including specifying the uncertainty of the forecast. So ensemble of forecast by varying rainfall forecast model, if you have another model, or by changing key parameters that inducing uncertainty in the hydrology and hydraulics. So uncertainty, when you give forecast, uncertainty, some band of confidence in a reverse way, you have to provide. Enhanced awareness creation that the countries will gain more if they invest in a sustained way in flood forecasting, flood mitigation preparedness, and well-planned and real emergency response. We have to show this clearly. In yesterday, World Meteorological Organization presentation, the return for investing in flood preparedness is like 1 to 10. If that solid information, we might inform the decision makers. Investing on flood preparedness and mitigation is very valuable. The National Flood Forecasting Center should build their capacity in individuals. This is an important aspect. Expert skill and knowledge. So you need to invest on individual. Organizational aspects, regulations, manuals, infrastructures. This is more or less for time being intro is doing, but the the country should also carry over this one, sustain it, and its enabling environment. National legislation, economic systems that makes few demandable. In essence, for example, the road authorities should buy your forecast, because the irrigation, the irrigator should buy your forecast product. To make it sustainable, there should be economic value for your forecast. So this will make it more sustainable in the future. And thank you very much for listening.
Thank you very much, Professor Ilma, for your excellent presentation. Now we go to the next presenter. The next presenter is Ms. Millie Muluro. Ms. Millie is from Nile Equatorial Lake Subsidiary Action Program, Kigali, Rwanda. Millie Muluro has a master's degree in integrated water resource management from University of Dar es Salaam, Tanzania. She has almost 20 years of experience in the Nile Basin region, with special focus on use of Earth observation data for water resource management and river basin monitoring. She took lead in the development of the Nile Basin Water Resource Atlas, was a key contribution to the Nile River State of Basin report, and pioneered the preparation of the quarterly bulletin on the monitoring the Nile Basin using Earth observation data. She led the development of 2 web-based geo-tagged management information systems to support access to and visualization of georeferenced water for agriculture infrastructure information for Uganda. She supported the identification and the promotion of the use of suitable climate data sets for early warning to last mile farmers in Eastern and Central Africa. Currently, Millie is taking a lead in development of a flash flood early warning system for the Nile Basin countries under the Nile Cooperation for Climate Resilience Project funded by the World Bank. The title of her presentation is Application of Operational Flash Flood Early Warning in the Nile Basin Countries. Ms. Millie, welcome. Please, you can start your presentation. Thank you.
Thank you very much, Zaleke. Good afternoon, everyone, and good morning to those not in this region. As Zaleke mentioned, I'm the Water Resources Officer, GIS Modeler at NELSAP-CU. NELSAP-CU is an investment arm of the Nile Basin Initiative. We are based in Kigali, Rwanda, and we are in charge of water resource management and development in the Nile Equatorial Lakes region. And as Zeleke mentioned, my presentation will be on the application of operational flash flood early warning in the Nile Basin countries. We know that from experience, since we live in this region, we know that our region is experiencing a lot of floods. There is a report that shows that there has been an increase in flood events by 23% between 2000 and 2019 in the Nile Basin, globally. But we also have seen some of these events in the Nile Basin region in some of the countries. For instance, in DRC, Congo, on the 4th of May, there was a huge flood that led to loss of lives and loss of property. We see another flood that happened still in DR Congo in January 2022, and we see people displaced after the flood from their homes. We see Narok. Narok has become a celebrity in terms of flood, and you can see the kind of chaos that comes with these floods. For Narok, this is a flash flood event that resulted and caused all this chaos that you see in this picture. We see similar floods taking place in Burundi. Burundi is also part of the Nile Basin region, and this picture was taken in April 2020. We see how the floods are displacing people also in Kenya, in the Nyando Basin, that is in the western part of Kenya. We see this picture also taken from Tanzania, Dar es Salaam. This was a picture taken last year in April 2022. So we can no longer say that we don't have that. The evidence is here with us. And so what can we do as the Nile Basin Initiative? In our response to this, now that we know that floods are here with us and there's something that we have to do about them, the NBI, the Nile Basin Initiative, is implementing the Nile Corporation for Climate Resilience Project, that is the NCCR. We are implementing this project for 5 years with 2 other agencies, the Lake Victoria Basin Commission and the Nile Basin Discourse. The NCCR is organized around 5 thematic areas, and one of the thematic areas is flood and drought risk mitigation. I also forgot to mention that this project is funded by SIWA, who are also the funders of these webinars. They partnering with NBI to fund these webinars, and they are also the same agency that is funding us to implement this project in the Nile Basin region. For the flood and drought risk mitigation thematic area, which is just one of the components of the 5 thematic areas of this project, we aim to enhance preparedness and resilience of Nile Basin countries against flood and drought disasters through decision support services. If you have been following the previous webinars, the previous presentations in the first 2 days, a lot has been said about early warning for all as a global agenda, the UN global agenda. And so we are also contributing towards this. And we are developing a Nile Basin flash flood early warning system. And this system has a geographic coverage of the parts of the basin and some parts of the basin, some parts of the countries within the Nile Basin region, but not covering all the Nile Basin countries. We'll get to that at a later stage. The previous presenter, Professor Yilma, has talked to us about their efforts in the Eastern Nile region, which are mainly looking at riverine floods. But for this particular activity, we are looking at flash floods. And when I talk about flash floods, these are floods that happen in very short period of time. They are very swift and they leave huge damage, because normally they are happening between less than 6 hours from the time of an intensive rainfall or long periods of rainfall. And so we need to alert communities about such flood events, about such flash flood events. And so we hope that with this system, we'll be able to support the national meteorological and hydrological services in the Nile Basin member states to obtain reliable and effective flash flood early warnings, especially for the flash flood prone areas. And we hope that in so doing, we shall have reduced damage caused by such flash flood disasters. And as I mentioned, we'll be focusing or providing flash flood forecasts for selected hotspots. And so we had to start by identifying the hotspots themselves. And we did this through country consultations. As we are implementing this, we are working with the technical working group members, and these are members coming in from the different countries in the offices in charge of water affairs. But we also consulted the officers in charge of disaster preparedness in all the countries, and we also consulted the Met offices. And in these consultations, we needed to know, for instance, where the flash floods occur, and when they occur, what do the countries do? What do the countries respond? How do they respond? What do they do? Who is in charge of this? Who? So that we can identify the roles and responsibilities in managing floods. And we also interacted with the communities. As I mentioned earlier, we are working with the Nile Basin Discourse The Nile Basin Discourse is a civil society that connects us to the communities, to the vulnerable communities. And when we went to the countries for the country consultations, we interacted with the communities, with the vulnerable communities. The intention was to find out, do they actually receive any early warning information? Have they ever received any flood early warning information? And if it came to them, how was it received? How was it perceived? Did they respond? Because it's one thing to send out an early warning information, and it's one thing for the communities to respond. And would they like to receive this kind of information? So we interacted with the communities. We assessed the kind of dissemination channels they use, the capability to understand and know that this is an alert message, and will they be able to take it serious? So we have interacted at that level. But in addition to that, we have also, in a special environment, identified flash flood hotspot areas using flash flood indicators. And we have all these maps where we have identified where flash floods can occur. This is a map of Ethiopia. We visited some of those hotspots, and we could see the kind of damage that the flash floods do to some of those areas. So we have this for all the countries in the Nile Basin region. We have been able to identify the hotspots, the flash flood hotspots, and these will constitute the flash flood early warning system. So we have all these, and we have a detailed report that can be shared. As we interacted with the different agencies in charge of all those related to flood management, some of the findings are that we are all at different levels in the Nile Basin countries. We are all at different levels. Some countries are more advanced than others in terms of flood early warning, prediction and information provision, but some countries are still lagging behind. And this is a regional organization, and this is where we get together to carry and help each other to work towards a common agenda or to solve a common problem. As you can see in these pictures, this was an interaction in Ethiopia with the National Meteorology Agency. And here we interact with them to understand the kind of data sets they use, the kind of models, but also to understand the capacities in the different countries, the technical capacities, because it's one thing to produce a system that cannot be used by the people we intended to be used. So we had all these interactions, and we also identified the people that we will train to use the system. The other thing that we discovered is that there's lack of a comprehensive early warning system that can provide timely information about potential flash flood events. We have seen in the countries that mainly the countries that have tried to have systems have them on the rivers to show or to predict riverine floods, but not flash floods. But as I mentioned earlier, we also have to give flash floods attention because they happen so swiftly, and they leave behind great damage. And so we have to think about it. We also discovered that the countries use national weather predictions. This has its own challenges because we know that most of this is not at national level, and we know that when a weather event occurs, it's not restricted to national boundaries. And so this is where we come in as a regional organization, so that now we can at least have regional weather predictions, but not only do they stop at, and we don't want to just stop at weather predictions. Now we want to go ahead and predict the flood. So we discovered that in the countries, we just stop at national weather predictions. And so we want to take it a step further so that we make sense of what comes if the weather has been predicted. What then does it mean in terms of flash flood early warning? The other major discovery that we found out is that after some of the countries, most of these countries actually produce some early warning information. But how is it disseminated to the communities? We discovered that it is normally prepared by the technical experts in the ministries, those that prepare them, and then they will be sent out by emails. But how do they get to the vulnerable community? And that is one cause of concern that we need to address as we work towards the global agenda for early warnings for all. And so we are working with DHI. DHI is a firm that is helping us to develop the flash flood early warning system. And it's going to be a web-based system that you will be able to access from the NBI Integrated Knowledge Portal. Its interface will be similar to the river flow forecasting, since this was the same firm, DHI, that produced this as well. And so in terms of navigation, if you've been familiar with the river flow forecasting system, you will still be able to navigate through the flash flood early warning system for the Nile Basin countries. We have not yet prepared it, but we know that we expect it to be out by March of 2024, that is in the next year. And we'll be able to release flash flood early warning information for the selected hotspots. And these hotspots are agreed upon by the countries who are represented by members of the technical working group. And so we'll be able to send this information that will be displayed in terms of maps and charts, but the messages will come out as text, as messages. And so these will be sent out in the existing national dissemination mechanisms. As you can imagine, the NBI may not be able to connect to the vulnerable community, but we expect that the countries will play their role as a major stakeholder to send out this alert information in the existing dissemination channels. We will have lessons learned from the different countries that are doing well, and we hope that when we bring the countries together, the countries will learn from each other, and we shall share experiences to improve how we are disseminating information in the different countries. This is just a snapshot of what it will be like in the system. Basically, the small catchments where the flash floods occur will be given a color according to a certain alert level. This is not how it's looking like, but this is a snapshot of how it will look like. As I mentioned, we are in the process of developing the system. What are some of the opportunities as I conclude, as we implement this project? As we develop the system, one of the opportunities that lies ahead is that we'll be training the technical experts on how to generate this early warning information, and also to run the system at country level, even if it is a regional system. And so we planned a series of trainings, and we'll be training people to run the system and to operate it at national level. But also not just the technical experts, as you may have known by now that there is a gap between the technical experts and the communities. So we have also planned to create awareness to the vulnerable communities that we identified as we mapped the flash flood hotspots. We will build their confidence to trust the early warning alerts, that when they come, they will move. What does it mean to receive an alert? And when you receive it, what should we do? What should you do? So we are going to work towards preparing the communities that have been identified to receive these alerts. And in addition to this, after we are now starting the identification of suitable investment options to mitigate these floods in the Nile Basin countries, as we identified in the flash flood hotspots. And this is not going to be limited to structural interventions, but we are also looking at non-structural interventions. What can be done to prevent these floods? What can be done to mitigate the effect or the impact of the flood, of the flash flood? And so we are not only just providing early warning information, we are also working towards identification of investments, which will then help the countries to implement or to develop. And these will be both structural and non-structural interventions. What are some of the challenges that we have seen or that we anticipate As I mentioned, there is a gap between the technical experts and the flood-affected communities. What happens is, what we have noted even in the countries, is that the information is prepared, and we are talking of flash floods. We are talking of a flood that happens within 30 minutes from the onset of the rain. And so this information has to get down to the community on time. And so we have to work together as different stakeholders to make sure that after the technical expert has prepared this information, it's taken down to the vulnerable community. So this is one of the challenges that we have seen, and that is one of the challenges that needs to be identified, because we see that the system or the mechanism of sending this information is slow and many times bureaucratic. Imagine that if an officer has not turned up to office to run the system, then it will not send out the early warning information, the alert, or they will not run the system, and so they will not generate the alert. And so we all have to work together and to have these early warning systems work or achieve their intended benefits. And as I end my presentation, my call to action is I continue to encourage the countries to explore transboundary solutions through supporting joint analysis when the NBI reaches out these potential areas. So encourage the countries to support us as we carry out joint analysis. We encourage you to carry out joint planning in a transboundary context, and also to implement climate resilient interventions as we try to address the climate risks. The other call to action that I have as I end my presentation is to improve the preparedness of the vulnerable communities by creating awareness about the early warning systems. It's one thing to prepare the systems and they stop in our desks, but we need to go a step further to prepare the vulnerable communities. And we need to bridge the gap between the science and the communities. It is our responsibilities as people on this call, as technical experts on this call, to work towards this, to disseminate the early warning information. Once it has come to you, it is your responsibility to make sure that the vulnerable community receives this early warning information. And we can only do this in an integrated approach where we come together as stakeholders and share this information. I trust that the flash flood early warning system that is going to be developed by DHI, the science is okay. But what happens after the science? There is still a gap. So my call to action is that we need to bridge that gap between the science and the communities, so that the communities will benefit from all this work that we have done behind the scenes. It's a lot of work. And if we just keep it in our computers, we will not have helped the communities that we aim to serve. And with that, I thank you for listening to me. Back to you, Zeleke.
And answer questions accordingly. The next presenter is Dr. Bayene Makuria from DHI. Dr. Makuria Bayene has a career as team leader, modeling, and a DSS expert on water resources management projects in both Africa and Europe during his 35 years of work within the water sector. During his career, his focus area has been on the design and the development of different types of water resource information systems and the decision support systems. His professional profile includes experience in the area of engineering hydrology, data processing and analysis, hydrological and hydrodynamic modeling, flood and flow forecasting, flood risk assessment, development of database systems, as well as design, development, and implementation of decision support systems. His regional experience in Africa includes Nile Basin countries, the Zambezi Basin, and South Africa. The title of his presentation is Decision Support System for Integrated Water Resource Management in Tanzania. Dr. Bayene, thank you again for joining. Please, the floor is yours. Go ahead and present. Thank you.
Good afternoon, good day, ladies and gentlemen. My name is Makura Bayene. Thank you for having introduced me and having given me the opportunity to give this presentation. As mentioned by the colleague, the title of my presentation is an experience of a project that we're making in Tanzania. Before I go to the details of my presentation, I would like to make use of what Professor Yilma and Ms. Millie have said. Basically, I'm happy that I am following their presentations because any successful system requires 5 things to be in place. And I think that became apparent in both presentations. Any system requires 5 things: quality assured information, meaning data; modern information management systems, meaning software; scientific analytical tools, meaning methods; robust information technology and communication; hardware infrastructure, meaning technology; and skilled technical staff and decision makers, and knowledgeable stakeholders, people or institutions. These things have been covered to different depths by the different speakers before me. So I'm happy that I can now go into details on the second aspect, meaning software, modern information management systems, and partly I will touch, of course, the other aspects, but I'm happy that my presenters have gone into the details of those aspects of any system, especially forecast systems. The outline of my presentation is, I'd like to just present to you what the government of Tanzania is focusing on when it set up the development of what is called the ODSS, the Operational Decision Support System. And this Operational Decision Support System is a very comprehensive system that covers four themes or 4 topics in integrated water resource management. One is RIS, the water information system. The second one is a flood early warning system covering riverine and flash floods, the FUSE. Then we have a water use permitting analysis tool, the WUPA. And then we have the 4th system component, meaning dam operation support tool for reservoir operations. I have slides for all 4 components, but I will put more focus on the FUSE part. But showing the other parts of the system makes sense to show you what that integrated solutions matter when it comes to forecasting, when it comes to decision making in the water sector in general. The government of Tanzania has a program called the Water Sector Support Project. We are now in phase 2. It has been extended now. It was supposed to end last year. And the project comprises IWRM component, which includes the development of what I just mentioned, the Operational Decision Support System, linked to a modernized hydromet monitoring system. This again reminds us of what Professor Rima told us. Any kind of water resources decision-making requires modern and reliable hydromet monitoring systems. The objectives of developing this ODSS are twofold. One is to develop the RIS, the Water Resource Information System, to give linkage to hydromet data, to have integrated data management, analysis, and visualization tools, as well as provisions for embedding models. The other component, which is more comprehensive, is a system that has prediction tools for IWRM of the aforementioned components. A flood early warning system in the Wami-Ruvu Basin. I'll show you in a map where that is. A water use permitting and water allocation system in the Pangani and Rufiji Basin. I'll show you in a map. And then we, like in the piloting, decision support tools for reservoir operations for 3 selected dams in the Pangani and Rufiji basins. This is Tanzania. Opla. Tanzania, Zanzibar, Dar es Salaam here. So the Pangani Basin is in the northeast, where you have the Pangani River. In the north, you have Moshi, where is Kilimanjaro. So the Nyumba ya Mungu Dam is located here, not far from the border to Kenya. Then we have the Rufiji Basin, where between Dodoma and Iringa, we have the 2 dams called Tera and Kidatu dams on this river stretch where my mouse shows. And then the flood forecast system that we have is in the Wami Ruvu Basin, which includes Dodoma and also Dar es Salaam. The picture that Ms. Millie showed us on Dar es Salaam, I'll show you the forecast results on that. As a coincidence, I have some interesting, I have one screenshot of that forecast of the last rainy season, from the last rainy season. And then we have this water use permit analysis tool for the Pangani Basin and the Rufiji Basin. So we have those 4 components. So the purpose of the RIS is to enhance knowledge by sharing water data sets, knowledge products, and to provide easy access to any kind of water resources information across Tanzania. When I demonstrate to you, I'd like just to give you some screenshots of the system because, as I said before, my focus will be rather on the software part to demonstrate to you how software can help us making decisions and how it can help us to get a good overview over what we want to know. This RIS is linked to diverse data sources. It shows latest data from external and internal sources. It could be from public domain, from affiliated institutions like the Tanzania Meteorological Authority, from own data repositories. For example, the government of Tanzania is organizing its hydromet data in a separate database management system, so it has to be accessed from this decision support system that we're developing here. And then we need, of course, access to all types of relevant state variables that we need for water resources decision-making, historical, near real-time, and forecast data sets. So to give you an impression, we have a web-based system. Ms. Millie mentioned it before. It is the same framework that we're using for similar projects worldwide. In this case here for Tanzania, we have here access to their database, which is an Aquarius database. So you have a web-based, map-based system where you can see the stations, where you can zoom into the time series and analyze the time series. And for example, the analysis of time series could be like determining the probabilities of exceedances, or also called making duration curves. You can visualize animated graded information. In this case, we are here demonstrating the mean daily rainfall of a selected year so that the user can easily swap between different information products and visualize them and compare them, all in a web-based system. So next component is the fuse. So the fuse, and I'm happy that Professor Ilma had very comprehensive slides on how the chain is from the weather forecast to the dissemination. So I can give you just on one slide the overview. Every fuse builds on a weather forecasting system using numerical weather prediction models with QPFs, quantitative precipitation forecasts, from, in this case, from the Tanzania Meteorological Authority. So they make the forecast and then they avail it to the ODSS on a specific server. Based on that, the system conducts automatically hydrological forecasts using rainfall runoff models. So it converts rainfall into catchment runoff, and then with hydrodynamic modeling, automatically flood forecasts are produced for water levels and flows in the river system of interest, specifically for the flood-prone areas, selected flood-prone areas in the Wami Ruvu Basin. And then if this goes along exactly with what Ms. Millie said at the end, so what? When you have produced everything, what do you do with it? You have to inform and the stakeholders so that the appropriate actions can be taken. So any fuse must at the end have a dissemination system that gives the right information to the right people at the right time. This was also emphasized by Professor Yilmaz's presentation. So to automatically alert stakeholders through different communication channels. So again, coming back to what the software looks like in the web-based system, imagine an operator sitting in front of his or her computer, gets an overview of this is the Wami Ruvu Basin, part of it, the upper part, and you see certain locations have been highlighted red, catchments are delineated, and then you can, when you click on certain objects, you can, for example, see the forecasted catchment rainfall. Then you can, through toggling on and off, visualize the catchment runoff. Behind this is, of course, lots of scientific methods. As I mentioned, any system has 5 important parts to be fulfilled, and one of them is the methods. And here, again, it's about the software. So catchment runoff, you can visualize. And then you can, from the hydrodynamic models, then visualize also the water levels. Here you see the water levels visualized together with the thresholds, that if they are exceeded, we have different levels of alarm, the yellow level and the red level in this case, at a specific location in the upper part of the Wami Ruvu Basin. These are forecasts that we generated the last rainy season. I think, as far as I remember, must have been sometime in April of this year. Yeah, it's written there, I can see it now. Then you need to be able as an operator to configure any dissemination system, where at what level should the system make a yellow alert or a red alert. So the system allows you to define that for selected locations. Determining those thresholds is a science in itself. It is not an easy task. It incorporates hydrological understanding, field visits, discussing with the people in the field, the local communities, but also scientific parts, as I mentioned, statistical analysis of the hydrology of the region. And bottom line is you have to be able to easily define these thresholds in the system, which you can see here can be done interactively. Here we are in Dar es Salaam, so we would like to explore the flood forecasts. And for example, here, this is the Morogoro Bridge, which is a bit upstream of what Ms. Mili showed us. This is the Msimbazi River. The location where we saw the photo from is here downtown, but Dar es Salaam, where every year we have floods at that bridge. And then you can see the water levels here animated as a time series. In this case, the thresholds were not exceeded, but then you also can generate a longitudinal profile so that you can see how the flood propagates and along the river from upstream to downstream. So you can animate this. Now I just made a screenshot here of the water level at a specific time. In this case, 12th of April at 3 o'clock in the afternoon. Then comes the next level in a fuse, where you disseminate the alerts. In this case, I'm showing you the alerts are disseminated via email, and the recipients here are, for example, selected stakeholders, decision makers in different government offices, but we also disseminate similar messages via WhatsApp groups, so that people in the districts, decision makers in the districts, get the right alerts. And as Professor Yilmaz said, you just don't send out all alerts to all people in the region. You send it to selected, well-trained people of disaster management in the region, in the districts, so that they can translate these kinds of information that we see now in front of us into appropriate action. And this, again, is an iterative process, because you may have false alerts or you may miss an alert. So this is a very sensitive issue that also requires attention, and requires time also. From one rainy season to the other, you learn. Now let me a bit go over the other parts of the system a bit faster, because it's not as relevant, because we're focusing here on flood forecasting. So we have what we call the WUPA, the Water Use Permit Analysis Tool, which allows water allocation decisions. So if an irrigator makes an application, I want to use so many million cubic meters per time unit, let's say per week or something, can I do that? So the ministry or the basin water boards must be able on a scientific basis to give a grant, yes or no. There is a user interface on the same system where you can see where is which user, current ones, and where are pending permits. You make the necessary exploration and analysis. In the back end, you have a water allocation and balance model, and then the system gives you a recommendation whether to grant a permit or not. And then, of course, through human intervention, at the end of the day, it's a human who decides whether a grant has to be given and gives a recommendation in the business process in the institution. Then we have what we call the DOS. It's the Dam Operation Support Tool, which again is based on a forecast, hydrological forecast, but not short term in the range of 3 to 7 days, but rather seasonal from 3 months to 6 months. And one of the screenshots shown to us was by Ms. Milia then was the RFFS, the Nile Basin River Flow Forecasting System, also mentioned by Dr. Mudazzar at the beginning. It's the same principle here. We want to support dam operators to investigate what would happen if I change dam release rules. For example, what would happen if in the next month I change the target power because I anticipate, because of the forecast, that I would have too much water or not enough water, and then I can then investigate the effects downstream. In this case, the effects of the Terra Dam on the Kidatu dam downstream, how then would be affected the flows downstream. You can then have a dashboard where you compare different scenarios of what ifs, what would happen if I change inputs in forecast mode, in seasonal forecast mode, and then you can see how it would affect the energy production, how it would affect water levels downstream, and how and what the inputs are. In this case, we have defined the target powers as as input variable, as decision variable. So the as an overview, before I finish, the ODSS is an integrated solution that has these 4 components. I emphasized the FUSE, the flood early warning system, but the other components are equally important, especially the RIS. It's a must. You must have a water resources information system for any kind of decision making. And the DOS is something that we all need also in the Nile Basin, which is also based on forecasts, but rather long-term forecasts or mid-term forecasts, 3 to 6 months. And the water use permit analysis tool is another decision space in the water sector. So in my last slide, I'd just like to give you from literature, where are we when we talk about decision support systems? If you are in a completely unsupported environment, you don't have data, you don't analyze it, but you just make a decision. It's like throwing a dice. But then you have data provision through, for example, JSON database, data analysis through models. Options are generated through models, decisions can be selected by models, and decisions can be implemented also by models. So the last one is something automated. It's like the autopilot of an aeroplane. That's not where we are. We rather see that the ODSS and any forecast system, flood forecast system, flow forecast system, flood could be riverine and flush, is somewhere between where the system analysis gives you alternatives or the system gives you overrides. As you have seen in the UPA, the system may recommend to you whether you grant a permit, yes or no, but at the end, it's the human intervention that overrules everything. And in other cases, the decision maker must see the different options and make decisions. So with this, I conclude my presentation. Thank you very much.
Thank you very much, Dr. Dayene, for your comprehensive and impressive presentation. Now let me give the floor for Mr. Mohammed from Sudan, if he has connection. Mr. Mohammed, are you there? Can you hear me? Mr. Mohammed, you can go ahead and give your presentation.
Hello.
Hello, put it on a presentation mode, Mr. Mohammed.
Do you hear me very well?
Yes, we can hear you. We can hear you. Please speak loudly as much as possible.
Okay. Yeah, okay. I'll do my best. Yeah.
Yeah, now it's very good. Thank you.
Go
ahead, please. Yeah.
Okay. Okay. So hello everybody and good afternoon. Assalamu alaikum. Dear panelists and presenters and participants of the 7th Nile Basin Development Forum, and especially the participants of this session. So we're back in Khartoum, Sudan, story. So my name is Muhammad Adil Hassan, a water resources modeler at the Ministry of Irrigation and Water Resources of Sudan. So let's get started. First of all, let us start with a basic introduction and motivation on why this problem in Khartoum, Sudan's capital, is very important. So as you may know, climate change amplifies Sudan's floods, impacting, according to the UN OCHA, impacting an average of over 200,000 people annually. These floods are mainly from the Ethiopian plateau via the Blue Nile. So despite Sudan's typically arid climate, so unpredictable rain patterns bring increased flood risk and worsening socioeconomic issues in Sudan. So please check out this chart, which is displaying Khartoum's annual maximum water levels since 1980. So you can see clearly from please, do you hear me? So you can see clearly from the trend that the frequency of floods has been steadily rising. You can see it clearly from here. And even in the last decade here, in this part, even in the last decade, the floods has been almost every year in this part, unless 2015, because it was dry season. So, so also another thing, these floods also became lasted. You can see here from this chart, which represents the number of days above the flood level in Khartoum. You can see the flood level here is 16.5 at Khartoum Gauge Station. When the water overflows the main course of the river in Khartoum Station. So this is the number of days above the flood level. The blue one represents the number of days above 16.5 meters, and which is considered as the flood. but the orange one represent the number of days above the 17 meter in Khartoum station, which a danger level cause more harm for people and properties. So you can see here the flood of 20, which has the most highest in the last 100 years. So what happened exactly in 2020 and what was the impact? So,
Yeah, Mohammed, Mr. Mohammed, we cannot hear you now. Okay. Mr. Mohammed, we cannot hear you. Can you hear me?
hear me now? Hello?
Yes, yes, now we can hear you. Continue, please. Mhm.
Okay. Sorry for that interruption.
Yeah, we understand. We understand, no problem.
Okay. So during the flood of 2020, the Blue Nile reached its highest record in the last 100 years. And actually that level, it was 1.16 meter higher than the flood level. And 1,000 homes and properties have been damaged, and some partially and some totally, and many lives have been lost, and more than 100,000 people are affected during 2020 floods. Also, according to the satellite data detection, about 500 square kilometer of inundated land are inundated by the floods of 2020. So now I would like to, I don't know what happened.
We can hear you. Continue.
Okay, but there is some problem with my presentation. I will share my presentation again. You see my screen now?
Yes, we can see.
Okay. Oh, no, I can scroll my presentation. I can't scroll my presentation. I don't know what the problem, but I will reshare my presentation again. Sorry for that.
So Mr. Mohammed, please unshare so that we can display for you from this side.
Okay, so please proceed.
Can you see now the screen?
Yeah. Yeah.
Okay. So when you finish one slide, you can ask just to go to the next slide, okay?
Next, please. Next, please. Next. Next.
Yeah. Can you see now?
Yeah. Yeah. Thank you.
Okay.
So now I would like to share to show you some pictures from that devastating flood. In this image, let me try to use the mouse to show you. Can you see my cursor? Hello?
You cannot do that from that side, from your side. Okay. You just press. Yeah, you just press it.
Okay. Okay. So in these pictures, you can see a lot of stories of that flood occurred in 2020. Some of these pictures, the landmark are totally concealed, and it is difficult to distinguish between the Nile and the land. And you can see also houses and large areas are submerged in water, navigating the city, acting like a car, maybe. And but despite all of this, the prevailing theme was people coming together to combat this disaster. And you can see the biggest photo, which represent the photo from Tuti Island. From Tuti Island, young boys trying to block the Nile from entering their island by using their hand and the sandbags and so on. Interestingly, this image inspired a famous Sudanese artist named Sayyid Khalifa back in 1988 to this topic. Yeah, he was in who tried to block the Nile from entering the Tuti Island. So, and after that, all damage, the government declared the state of emergency for 3 months. So the next, please. I don't know if you hear me or not.
Yeah, we are hearing you. We can hear you. It's very clear and loud.
Okay.
Thank you.
Okay. So the next slide, please. And all these damages and massive damages was in our mind that we have to use an integrated and innovative approach for the upcoming 2021 flood season. So in that time, our goal was not to prevent the disaster entirely, but to minimize the disaster as much as possible and to minimize the harm and losses it causes. So the next slide, please. Or let me try to reshare screen again and share it yourself. Yeah.
Yeah, try from your side. Okay. Thank you.
Thank you. Thank you for your cooperation. Now you see my screen?
Yes, yes. Put it on the presentation mode and then continue.
Yeah. So the study area. So our study focuses on Khartoum, which is located in the heart of Sudan and which had the most impact of 2020 floods. Khartoum State, where Sudan's national capital, has experienced significant population growth and urbanization. And actually, the current population around 10 million people. Also, in our study area, the Blue Nile Basin, which originates from the Ethiopian Plateau and joins the White Nile here in Khartoum. So the Blue Nile has the seasonal character with 70 to 80% of its flow occurring in just 4 months, and totally contribute to the whole River Nile by about 60%. And here you can see here the the green feature here at the border. It's called the dam station, which accumulate the whole upper Blue Nile catchment here, accumulated at the dam, and the dam represent the inflow to the Rosiris Dam. The Rosiris Dam is the most upstream dam in the Blue Nile in Sudan. Actually was constructed in 1960s and heightened later by 10 meters in 2012. Actually, this heightening effectively doubled the reservoir volume from 3 billion cubic meters to approximately 6 billion cubic meter as an active storage. So this most upstream dam here, Osiris Dam, plays a key role in our study and our integrated approach. So we came to the methodology. In our studies general framework, our primary goal was to effectively mitigate flood risks for Khartoum using Osiris Dam. And actually, to achieve this, we required precise and timely forecasted inflow to Osiris Dam with reasonable lead time and sufficient lead time. And to attain this data, we employed one of the famous data sets called CHIRPS GFS rainfall data set.
Your slide is empty.
Yeah, not yet. Okay.
Yeah.
Can you see now?
Yes. Yeah, it's coming now.
Okay. So we employed this CHIRPS GFS forecast. It is rainfall forecast, and it is a 15-day rainfall forecast and updated daily. Actually, it is a modified version of NCEP, Global Ensemble Forecast System, GFS, and bias corrected towards CHIRPS dataset. This dataset motivated us to be used and utilized on a calibrated and validated rainfall runoff towards CHIRPS dataset. I will show you the calibration and validation results of this rainfall runoff model later. But our rainfall runoff model that we have been utilized and used here, it's called MHM. It is a fully distributed and grid-based model, hydrological model, and model was driven by its open source nature and its accuracy, and it is accuracy of simulation for the rainfall runoff processes has been previously validated from our previous work experience. So the model configured using the level 0 data, I mean the DIM and the land use, land cover, and the soil data, and so from the publicly available data set, and the model forced hysterically by CHIRP's data set. So this is for GERD. This is to simulate the inflow for GERD here. So now we have GERD inflow from lead time 0 to lead time 15 days ahead, and this is inflow at GERD. But we are not interested in the inflow at GERD. We need to the forecasted inflow at Osiris. Then to do that, we have actually we use a basic water balance method for the GERD, and we do a GERD water balance relying on publicly available information like gate openings and area volume height relationship and the height of the middle section and so on, to predict actually the outflow from GERD. Yeah, from GERD. So this outflow represents the inflow for them, and the inflow for them represents the inflow for Osiris. This inflow, it is a 2-week lead time. So as you know, we recognize that longer lead times reduced accuracy. So we depended only on 1 week ahead forecast instead of 2 weeks forecast, and update our model on daily basis. This is just for accuracy purposes. Then at daily meetings of the higher flood committee, they are in Sudan, they are a higher flood committee meeting. They meet every day and discuss and analyze these forecasts for Osiris Dam, and they discuss and analyze these inflows for Osiris and their impacts on various scenarios concerning Osiris Dam safety, downstream condition, and available capacity and available room at Osiris, and then determine the guided release for Osiris for the upcoming week. This release preferably be less than 650 million cubic per meter, unless there is a dam safety issue, there is a dam safety or room availability issue at Osiris. So we call this 650 million cubic meter we called it internally as a safe release. So why 600? Why specifically 650 million cubic meter? Why? Actually, we did the hydraulic assessment. We did the hydraulic assessment, a simple hydraulic assessment, not that much assessment that depends on hydraulic models and that and those cross sections and so on. No, we just do a simple hydraulic assessment of the river memory over the past 15 years. This assessment compared the maximum Osiris releases with Khartoum maximum water levels. This is the maximum releases from Osiris, yeah, and this is the maximum. This is the maximum water level on Khartoum for the past 15 years, and and historically we found that releases around 650 here in this part. Typically resulted in water levels around 16.5 meters in Khartoum, which is also considered as a flood level, but generally less, little bit danger than 17 meter, as I mentioned before, or above. So our objective was to prevent reaching to prevent Khartoum from reaching the critical level 17 here. So we will play here in this zone. Those are the results of the calibration and validation of the hydrological model that I mentioned. And these results are for the calibration period, and this the validation period towards CHIRP's dataset. And for those metrics, yeah, we use NSE and R squared and KGE and percent bias from for those metrics. And according to the DON 2002, the performance of the model was excellent. This means that the model is performing well and it is promising to be used for forecasting applications for GERD and then for Osiris inflows. So now the results. Let's take a look. The first result is the forecasted inflow at a day. This result is the first input, yeah, for our approach. It compares daily forecasted inflow at GERD and daily forecasted outflow from GERD. Yeah, this is the daily forecasted. The dotted black is the daily forecasted inflow for GERD, and the red one is a daily forecasted outflow from GERD, which represent the Osiris inflow at them, and the blue one is the actual observed inflow at them at that time. So here, this chart demonstrates to some extent how good, you can see here, how good is the simulation of daily stream flow. I mean, to some extent, how good is the simulation of daily stream flow at a day. Here, notably, you can see here that GERD at that time not yet overtopped, and the second filling is still there, yeah, of GERD. So after we ensured the goodness of the input of the inflow for the approach, now let's talk about what happened in Osiris. This chart shows the inflow and outflow and the average at Osiris during the 2020 and 2021 flood seasons. So this is the inflow of 2020, the red one, and this is the blue one is the inflow of 2021, and the black dotted one is the average inflow for Osiris. So the cumulative inflow of 2020 and 2021 here, from here to here, is a little bit similar until this point. But you can notice that in 2021, there was 2020. I mean, there was a huge late peak here. This one. Sorry for that. I didn't show the outflows. This is the outflows of the Osiris in 2021 and 2020. Regarding this huge peak, you can see here. Even this peak, Osiris successfully reduced reduced the late peak in 2020 by over a third. Yeah, Osiris successfully reduced this peak by a third. You can see here from the outflow of Osiris. This is the inflow, and this was the outflow from Osiris. And this reduction actually preventing further damage to Khartoum at that time. really we can't imagine how bad the disaster and damage will be compared to what it was at that time. So gratitude is expressed to God firstly, then Rosaries, and then the higher flood committee for their proactive decisions and immediate decisions and efforts during that critical period. Now, this graph illustrates the captured flows at Rosaries. This is the captured flows at Rosaries in 2020, the red one, and the blue one is the captured flows at Rosaries in the blue one. Yeah, you can notice that at this time here, Rosaries managed to reduce this peak totally. So, and Rosaries managed to reduce this peak by almost 20%. While in 2020, Rosaries managed also to reduce this peak, yeah, by almost a third. Yeah, it's actually 35%. So this happened actually by not exceeding the safe release from Rosaries, which was 650 million cubic per day. These captured inflows are reflected in Rosaries reservoir level here. This is the normal reservoir level for Rosaries, and this is the reservoir level of 2020, and this is the reservoir level of 2021. It actually shows that the Rosaries reservoir water levels in 2021 were significantly higher during the peak time here. This is the peak time here, this one. So you can see Rosaries here significantly was higher than it was in 2020. So this means more significant mitigation of flood peaks downstream. Also, this graph shows that Rosaries Dam passed the flood safely, while there is still room for exceptional peak. Yeah, here you can see there is still room here in 2021 for another exceptional peak if they are, and to be refilled again to reach the maximum full supply level. So our integrated approach and mitigation effort significantly led to a noticeable reduction in Khartoum levels. You can see here this is the water levels in Khartoum in 2020 and 2021. So you can see here. You can see here the number of days of water level above the threshold dropped from 16 days up to only about 44 days in 2021 compared to 2020. And also the water level decreased by about 40 centimeter in 2021 compared to 2020. So also we used a GIS assessment using Sentinel-2 satellite data. So we determined that in 2021, so the dark blue is the natural river, and the baby blue is the flood extent of 2021, and the red one is the extent of flood 2020. So we determined that in 2020, the total extent, the total flood extent was about 500 square kilometer, and it is significantly reduced by for the whole Khartoum state by a 53% reduction in flood extent across Khartoum state, and a remarkable when we zoom in inside the Blue Nile parts inside Khartoum state here. When we zoom here, we can see that a remarkable decrease, which represent about 74% in flood extent in 2021 compared to 2020. So, although our approach aimed for even more effective reduction in water levels in flooding, our analysis revealed that the impact was primarily limited to Khartoum, not the other Blue Nile reaches. So this inconsistency was due to the exceptional White Nile inflows, which significantly affected only Khartoum compared to other locations on the Blue Nile. So we did an examination of water levels for the Wad Madani station. It is about 200 kilometers upstream Khartoum, which were no significant tributaries downstream or dams downstream. So the pattern supposed to be the same. So the water level you can see from here, the water level from Madani here, from the water level from Madani in 2021 only exceeded the flood level. This is the flood level, only exceeded the flood level by a small margin of centimeters, and only for 1 week, while it was almost month and a half in Khartoum. Actually, this difference was attributed to the exceptional White Nile inflows in Khartoum. Also, I would like to mention that according to some reports from UNOCHA, the number of affected people has been significantly reduced from 100,000 affected people to only 4,000 affected people in 2021 compared to 2020. So we came to the conclusions and recommendations. So the conclusions, climate change is there. Climate change exists and caused massive floods and massive floods either through the rainfalls or either the Blue Nile or other tributaries. So and recently the Blue Nile also became exceptional. So climate change is there, and it is leading to more frequent and severe floods. So the application of an integrated approach guided by good inflow forecast with sufficiently time, hydraulic knowledge of the river memory, and take proactive and inclusive decisions from a roundtable discussion by using upstream reservoir proved effectively in mitigating flood risk in the study area, especially during the 2021 flood seasons. And this is the key results of using this approach is that the ones that I have mentioned before. So let us come to the recommendations. So we need actually to develop and enhance the national and regional climate resilience strategies that incorporate climate adaptation measures into water resources management to address the increasing flood risk associated with climate change. Also, given the increasing flood frequency and duration of flood in the region, it is crucial to enhance flood preparedness and response mechanisms, including implementing early warning systems and awareness raising.
Hello, Mr. Mohammed.
Yeah. So many thanks for your attention. So join hands with us to create a safer future for Sudan and the Nile Basin and even the entire world. Together, let us take adaptive and proactive practical steps to combat disasters and address the challenge of climate change. Thank you very much. So, Deliki, the floor is yours.
Thank you very much, Mr. Mohammed, for your excellent presentation. Now we directly go to the panel discussion. We have like few questions. Please, presenters, go to the Q&A and try to answer the questions there because it's getting late, so it's better to go directly to the panel discussion. So we have Dr. Khalid Hasbullah from IGAD. He is our moderator for the panel discussion. Dr. Khalid is a senior hydrologist at IGAD Climate Prediction and Application Center. He holds a PhD and MSc in water science and engineering from IHE Delft, Netherlands, and a BSc in civil engineering from University of Sina, Sudan. Dr. Khalid has over 20 years of experience in water resource management, hydroinformatics, flood forecasting, and risk assessment and response. Thank you very much, Dr. Khalid, for joining to contribute from your wide experience on this webinar. We have also two other panelists, Dr. Angelica Gutre from NOAA. She was supposed to join, but she has some challenge. Also, Dr. Rishad Kaladas from ICPAC. I think he couldn't make, but he was our, he was supposed to join as a panelist. Now, Dr. Khalid, the floor is yours. So all presenters, you will be panelists during this session. Please stay connected and share your experience. Thank you very much. The floor is yours, Dr. Khalid. You can go ahead.
Thank you very much, Zillaka. And thank you very much for the colleague at the Nile Basin Secretariat for giving the IGAD and ICPAC this opportunity to participate in this very important forum in the region. I have been part of this forum for many years. So thank you very much for giving me this opportunity. Again, my name is Khalid Hasbullah, and I'm glad to be the moderator for this session. So I have three panelists, Dr. Angelica Guterres from NOAA, and Dr. Nishat from the IGAD Climate Prediction and Application Center. Please allow him to participate as a panelist. I can see him, Dr. Nishat. And then I have also invited Mr. Omar Saleh. Is a managing director for a consultancy company from the Netherlands. They are providing around the innovative solution, maybe for flood management. I thought it's important to invite him to be part of this panel discussion. So I would like to thank him because he accepted the invitation in a short notice. So kindly also allow him to be part of the panelists, Omar Saleh. So I think we are very much behind the schedule, Zalaka. I don't know how we go for it. So how much time for allocated for us? Can we go maybe up to 5? Because now it's almost 4:30. So I will try my best maybe to make it shortly, but I would like also to engage all our presenters in the discussion as well, because myself, I have been enjoying the interesting presentation from all the presenters. So kindly be with us and so please maybe first allow me to forward my or to start my discussion with Dr. Nishad, because he has another commitment. So let me just start with him. Dr. Nishad, maybe one of the major issues from the presentation, I think the issue may be related to data quality and data accuracy. So maybe as a data science and machine learning expert, how can we deal with maybe information uncertainty challenges for both the input data and also the output products from our forecasting models? I hope Dr. Nishat, you get my question.
Yes, thank you, organizers, for inviting me. I'm working on impact-based forecasting. So the impact-based forecasting is actually a risk communication method basically. What it is communicating is basically the risk matrices, of how much is the impact and what is the certainty or the probability of that particular impact. So in that aspect, for this development, I could check that the importance of uncertainty, the data uncertainty, and how we can make the decisions based on the available data and its uncertainty involved in that. So what I found is that in the risk analysis and decision-making process, we can have a kind of in 3 levels methodology which can be employed. The first level is that we can use the deterministic models or the forecast, which is as we see that there are forecasts like WRF is being used, which is in downscaled version from the global forecasting system as in input data. And this setup is like a single observation or single forecast and make the decisions or assess the risk based on that single deterministic data what we have. And the second level we can use is the ensemble forecast. We can see that there are options being explored in one of the presentations where there is an ensemble forecast is being used. And this ensemble forecast is will give a direct empirical probability, and we can use Bayesian probability, especially in that case. If you are seeing the first level where we are using the deterministic forecast, we need to stick our probability definition to the frequentist probability, where we need to use our past observations to use the probability or calculate the probability from the past observations or past forecasts. So it has limitations, like as we can see that the level of water is seldom following the past. Using the ensemble forecast, which gives the Bayesian probability, which is actually a kind of the definition of Bayesian probability is very simplistically, we can see that it is an updation of the prior information with new information or new knowledge. And the third level is like that, which is looking for the storylines or looking for the alternative versions or alternative scenarios to access or assess the different scenarios. So this we can use it in, there are new concepts or concepts like climate, physical climate storylines, which is based on a ensemble forecast as an input data, but they generate the or use that ensemble forecast as in counterfactuals or downward counterfactual. We explore the kind of in worst case scenarios to be assessed and check for that how we can use or how we can have a risk assessment from that and make our systems resilient to that worst case scenarios. So with these three levels attached to the current deterministic forecast, we can address the uncertainty informations, and there are machine learning methods like Bayesian networks which can be used for the decision makings or recording the decision making and improve iteratively. That is the way we can use. In ICPAC, we are trying on that the second level of using ensemble forecast, like global ensemble forecasting system data as an input data, and generate hazard models, basically the same kind of an ensemble forecast like GLOFAS river flow forecast as an input data as well, which can be used for the impact calculations. And then if you are having a Bayesian networks based decision-making process, which can helpful to generate this final impact-based forecasting output, which is a simple risk matrices of the how the impact and what is the possibility of that impact. Yes, I close my answer here. Thank you, Dr. Khalid.
Thank you very much, Dr. Nishat, for highlighting the current effort by ICPAC in advancing the impact-based forecast. And yesterday, the International Federation of Red Cross and Red Crescent Society, the IFRC, related to the current, maybe the devastating flood in Libya. And part of that press release is a statement emphasizing the strengthen the emergency management and also improving impact-based forecast and also the warnings design. So thank you. Modeling. He mentioned the issue of data accuracy and data availability and quality as well, and also he mentioned the challenge of institutional capacity. But my question will be related maybe to the data, as you are a data science and machine learning expert. Maybe in absence of ground real-time observation, maybe how Earth observation, how open data can be maybe used to support the hydrological forecast and decision support system? And what is the reliability and accuracy of open data as input for hydrological forecast model and also to generate accurate and timely warning?
Yes. Regarding the hydrological modeling, so what we are intended to try is that in the impact-based forecasting, it is the contextualization of the impact where we need to convert the rainfall forecast, the amount of precipitation, into a ground level impact. That means we need to have the inundation data has to be generated, or inundation layer has to be forecasted, which we need to use hydrodynamic model, which is an extension of the hydrological model, but with then a shallow water equations or other simplified methods which can be used. So one of the major hindrance, as Professor indicated, the capacity related to that, which can be addressed using the modern machine learning or deep learning methods. The first method we can try is that we can have a kind of parsimonious models related to the hydrodynamic models. As Dr. Khalid is involved in the Down to Earth project, there are parsimonious model they developed for the hydrological forecasting, like drip models, which is a very simplified model, but it is computationally easier to forecast and computationally less cost to forecast can be to run the model and generate the hydrological river flow outputs. But similarly, there are hydrodynamic models are being explored with the same parsimonious modeling paradigm, where it is a simplified model of list flood FP, where they made the code base into a Fortran based method, and they made it into a very simplified model like RIM 2D. One of the model we are using it for that conceptualization of using the parsimonious simplified hydrodynamic model, where we can have a kind of an inundation forecast with the available rainfall forecast easily can be generated, and which can be used directly to contextualize the impact, and from that impact we can generate the impact calculations. The role of this machine learning methods in this chain is that once we are having enough sample of this parsimonious model, maybe in use of randomization or the deep learning methods like GAN deep learning method, which we are already using it for the ensemble forecasting downscaling and improving the resolution of the ensemble forecast, which can be actually implemented for this hydrodynamic model output, and which we can use it for a generation of the random or the improving the sample size of the different water levels, and based on the water levels, different water levels, we can have a kind of an impact or the risk assessment carried out, and make the disaster risk management based on this risk level, and make the decision based on that. That is an option available for using the deep learning and machine learning methods. Yes, thank you, Doctor.
Thank you very much, Dr. Nishad. I really appreciate that. So now let me go to Omar Saleh. Yeah, I have met Omar last year in Kenya, when I have been invited to attend the demonstration of an innovative flood defense solution. So, Omar, I think you have seen the last presenter, Muhammad Adil. I think he, in one of the photos, he shows like young people in Tuti Island. They are trying maybe to fight with the flood with just like traditional method using local materials. So I'm just wondering what is like the innovative new solutions and method that can replace those traditional methods and can be more effective for flood defense. Yeah, maybe especially you can refer to the slam dam solution. So thank you, Omar, for being patient with us. I told you that the discussion will be around 3:30. Now we are heading 5. But thank you for being with us. So the floor is yours.
Thank you, Dr. Khalid, for inviting me, and thank you all participants for being here. If it's okay, maybe I can share 2 slides, quick presentation, if that's okay.
Yes, please go ahead.
Yeah. Okay. So, indeed, I think I've seen really amazing presentations, and I think what I've seen today is something that I come across all over the world. Data is important. Early warning systems is important in each and every country. Data, by the way, also in Europe, here in the Netherlands, where I'm based, even that sometimes is scarce, is difficult to obtain. So it's a difficult subject. But it's very important. When it comes to early warning systems, I think it's an important measure. Everyone agrees, because we want to have early warning systems implemented all over the world. But an early warning system in itself doesn't prevent flood damages or drought damages. An early warning system is actually a trigger to take anticipatory actions, being evacuations or other types of measures like the ones we offer. So we are, as project developers, we implement projects all over the world. Indeed, with a new innovative solution, which is a mobile flood barrier that I will show you. But the first phase of our project always has to do with modeling. So what we do is we try to collect data. We develop hydrodynamic models. Even if there's the data scarcity, we do the best we can. And then we try to make the models for us to get an understanding of what can we expect, what kind of flood characteristics are there, what is the flood depth, what is the flow direction, what is the flow velocity. All this information gives us an idea of how our solution, which is called Slam Dam, how that could help with that region. So this is an example we did in Burundi, where it's in the Mapanda commune in Bubanza province in Burundi. Burundi itself, most of the issues they have to do with drought. But in the Imbo Basin, they have also flood issues. So that was our target area. What we did over there, Burundi also data scarce. So we heavily relied on the data that we got from local experts. So they did some field visits, tried to gather as much data as possible. We made a model for that. Based on that model, we had an indication of where should our solution be deployed in case of a flooding. We used 3DI hydrodynamic modeling software from a Dutch organization, Nederland Schuurmans, here in the Netherlands. When we did that, then the next we figured out, okay, now we know where to deploy our mobile flood barrier and the Slam Dam technology. What should be the length? What should be the dimensions? What we did is we manufactured the solution, sent them to the location, and trained people in less than half a day. They were fully equipped on how to deploy Slam Dam. I think that's an important feature of our technology, that it's very low entry. Yeah? We can train local communities who have no technical backgrounds, no educations. We can train them in less than half a day on how to deploy a Slam Dam. It's a very straightforward product, so that makes it very scalable as well. Because it's a manual solution, you can carry that manually with just a few people, as you can see here. And in a matter of a few hours, you're able to build a barrier of hundreds of meters. This is an example, like I mentioned, in the Mapanda commune, where we know flooding happens there in March and April. And we said, okay, let's use Slam Dam there as a semi-permanent solution, because the material is UV resistant, you can store fluids vapor tight. The only risk is vandalism or theft normally, but in this particular case, it's a tight community, so the risk there was lower. So we said, let's use them as a semi-permanent solution. So the dam is there being deployed for a few months during flood season, and it can effectively prevent flooding of the crop fields, because that normally floods they really damage the crops a lot, so they impact the community. Now we are able to protect flooding using that innovative technology. And in addition, what the community has been doing last year even came kind of to a surprise to us, but they've been using SlamDam throughout the entire year. So in March, April, they were using it for flood prevention, but then the rest of the year, they were using it as a reservoir to harness water. So actually, they doubled the agricultural production in the Mapanda commune. So it has a double function in our case. Even so, this is a solution that we offer. It's data driven. So we really, even now as we speak, we are doing an analysis in Isiolo, Kenya, because of El Nino. We know that there will be flooding, and now we're doing an analysis using the same software, same technologies. We are exploring, okay, where in Isiolo should we now deploy SlamDam, and hopefully shortly we will send it to Isiolo and then help prevent flood damages. I think one of the biggest advantages, if you compare SlamDam to other kinds of measures like conventional engineering works or maybe nature-based solutions, with us you have direct impact. So we send SlamDam and you can immediately use it and it's immediately effective. And that is a downside sometimes of engineering works, which takes a lot of investments, takes a lot of time. Even nature-based solutions can take 2, 5, 10, 20 years sometimes to be fully developed. And with us, with SlamDam, it's adaptable because weather patterns are changing, landscapes are changing because of urbanization. That means that the risk of flooding might also change. And because SlamDam is flexible, you can deploy them and dismantle them. You can reposition it to adapt to the flood risk. So that's what we've been doing now we've been quite active in Eastern Africa, and we would like to explore even more. So the next one, I think, for us will be then in Kenya and Isiolo to help with preventing flood damages from El Nino. It's in a nutshell.
Yeah, thank you, Omar. So for the benefit of the audience, so what is the magnitude of flood, maybe, or in terms of water level that maybe the SlamDam can accommodate?
Yeah, so currently the length is basically I want to say indefinite, because it's a modular system, so you can make the barrier as long as you want. Maybe that's even better if you can see it here on the picture on the right-hand side. So lengthwise, as long as there's enough space and the ground surface is not too much of a steep slope, that will be difficult. But other than that, the length that doesn't matter. If there's enough space, you can deploy SlamDam. For the height, currently, what we do, the max is 1.50 meters high, even though we are developing now a higher model. The trade-off is something to keep in mind, that if you want to go higher models or even lengthier models, the current ones are 5 meters length. But if you want to have lengthier models, the challenge is that they become very heavy, and then you cannot really operate them manually. And I think that's an advantage if you have, for example, communities that need solutions. They want to use manual labor. They don't have any cranes or heavy equipment to deploy a barrier that is 10 meters or 15 meters in length and 2 meters high. So we try to go higher as much as possible, but then the trade-off is that sometimes you might need heavy equipment. So, but the ones we have now you can operate them with manual labor easily.
Yeah, thank you very much, Omar. Please just be with us in case of any question from our colleague from the Nile Basin Secretariat. So I'm not sure if Dr. Angelica is here with us or not. If she's not here, maybe I would like to ask maybe the following question to Professor Yilma Selashi. So I think, Professor, you have talked about the early warning system enhancement in the Nile Basin area. So I'm just wondering if there is any mechanism in place to ensure that the warning system that you are providing from Intro, I know that you are providing this warning on daily basis. Even today, I received the report from Intro but the issue is about maybe the mechanism of the dissemination mechanism. So you are disseminating this maybe flood early warning report maybe among the scientists. So I'm not sure how what is other mechanism that can improve the dissemination so that this forecast warning can reach the last mile. Is there any effort, for example, in translating this in translating this forecast into maybe different language that can be more understandable by local users?
Thank you, Khalid. You are right. We disseminate every day, beginning July 1 to various stakeholders, the flood forecast and early warning. Our major claims to provide this forecast are the water affairs ministers, the hydrology department. So they receive that information, they use it together their own national forecast system to make a decision. So in terms of an institutional link, that is the direct provision of our forecast to the water affairs ministers of flood forecasting center. But other stakeholders, as you said, universities, NGOs, other government institutions, including your institution, they will receive to use it as it fits. What we wish now, in future, of course, we are doing it in our present project also. Our early warning, at least we create a system to reach the last affected communities at the community level, the right information of early warning. You can imagine to make this happen, starting from intro level, it's very complicated. It has to pass the national system, and then the national system has their own dissemination mechanism. That mechanism for flood early warning has to be set up correctly, and it has to function robustly, and the content of the forecast has to be also very clear when it reaches to the when it reaches to the community. So it's a complicated task. As an institution also, we don't have much push in that area because our forecast is regional, but necessarily you implement it at national level. So the interaction is not straight also forward. Thank you.
Yeah, thank you. Thank you very much. Maybe a following question. I think together we have seen the slum dam solution by Omar Saleh. So I'm also wondering if there is any innovative solution for flood defense currently in place within our region, so that maybe can be adopted in other places. Is there any innovative approach in place within our region right now? Maybe this question can also, everybody, I think, from the presenters can also come in.
So if I may say a bit on this.
Yes, please go ahead.
Once we made a visit to Khartoum this year, and Tutu Island, I think most of you know that, it's an island between White Nile and Blue Nile. So they are really, when you be in the site, you understand they are highly vulnerable to flood impact. So they were historically well organized to defend themselves. They have their own system, watch people to see if the water level is rising or not. But this time now they use a WhatsApp system to alert people. The flood lead man will alert his group of community, even in the night, to wake up and strengthen further by provision of dikes and so on, or moving to the higher ground to save lives. So the new technology of WhatsApp have been used. This is what we witnessed. Thank you.
Thank you very much, Professor Yilma. So I think we are running out of time, but if you allow me maybe to ask one last question, I would like to ask Willie. Willie, maybe in your presentation, you have ended your presentation by a very important point on the need for bridging the gap between scientists and users. I think this is a very good point. And I totally agree with you that even here at ICBAC, we are facing the same maybe challenge, because most of the time scientists are talking to each other, but there is no really like a link between the scientists and the end users, because we are a service provider. We provide it, we generate a lot of products. We are generating climate forecasts, but then how this climate information can timely reach the end users. So you have talked about the gaps and so I would like you maybe to more elaborate on what are these kind of gaps that we need maybe to bridge between the science and users, and what are the tools and mechanisms that we have so that we can overcome these kind of challenges.
Thank you very much for that question. Maybe I will share an experience as we carried out the country consultations in Sudan. We discovered that for them, flood management is centrally managed. And what they do is there's a task force that comprises of different stakeholders, and this is at the National Council of Civil Defense. So what they do is they have different people coming in from the different sectors, and these people are connected from top to bottom down to the communities. And they are sending this information using WhatsApp, using Telegram. And I saw that was somehow effective way of sending out this information to the community. We saw the same in Ethiopia.
Why?
Sorry. We experienced the same in Ethiopia. As we interacted with the communities, actually they could receive this information. But one of the challenges was that the information was for a very large region. So even when they received the information, then they would receive this early warning information, and then the challenge would then be they thought that the alert would be for Tuesday, and then the alert is coming on Thursday. So we still have a bit of that, but I realized that to bridge the gap, we really need to work. Every stakeholder has to play their role. Everyone needs to know what to do. We have to work with the officers in charge of disaster preparedness, with the civil society, with the Red Cross Society, because these are in touch with the communities. So as scientists, the technical experts, we need to now, as we develop these projects, as we design them, we need to remember that if our projects are not used, if our products are not used, then we are not being effective in our role in flood preparedness. That's what I could say, but we are yet to learn of more effective ways. We are also preparing a dissemination strategy that will be tailored and customized for every country. And we hope that we shall use existing mechanisms in the countries to disseminate this information to the communities using the existing mechanisms in the countries. Yeah, that's what I could say about that. Thank you, Khalid.
Thank you very much. So I think by this it's now 3 minutes after 5. So I would like to thank all our panelists. I would like to thank Omar Saleh for his time. I would like also to thank Dr. Nishad Kadalas and all the presenters for the interesting discussion and very informative presentations. I would like also to extend my appreciation to our colleague at the Nile Basin Initiative Secretariat in Entebbe for giving us the opportunity to be part of this forum. I believe that we are serving the same countries and also the same communities as IGAD and the Nile Basin Initiative. They are maybe serving the same countries. So thank you very much for this opportunity, and I would like to hand over to Zallaka to guide us for the remaining part of our program. Thank you very much.
Thank you very much, Dr. Khalid, for your great contribution. And I would like to also thank you for joining us with the two experts, the data scientist and machine learning expert. I'm very glad to hear from him about the challenges we are experiencing in the region as well as in the world on data and modeling exercise. Also, I would like to thank Omar Saleh also. Thank you very much. Thank you all presenters for your great contributions on this webinar. Now I'll give the floor to Dr. Mudassir to give a closing remarks. Over to you, Dr. Mudassir.
Thank you. Thank you very much, first, Zelleke, for the excellent moderation for this afternoon session. And it was a very good session about management of flood emergencies. And I would like to thank also all our panelists and speakers, Ms. Millie, Ms. Ajok, and Engineer Muhammad, and Dr. Mupriya, and Professor Yilma Silashe. Thank you all very much for the informative and outstanding presentation. I would like to thank also Dr. Khalid Al-Noor. You supported us yesterday and also today in moderating this panel discussion in an excellent way. We appreciate very much your support, Dr. Khalid, and the support of ECPAC. And as you said, we are serving the same communities and the same countries. And I would like to thank also Dr. Nishad and Omar Saleh, Engineer Omar Saleh, also for their valuable contribution. Also, we have our team here behind the scene, Mr. Sued Wamala, Patrick Rutuguera, and Christopher, and Ms. Marushka. They did also a lot of work behind the scene. Thank you very much also, our team here. And I just would like to invite our participants for tomorrow's sessions. Tomorrow we have two interesting sessions, one at 9 a.m. and one at 2 p.m. The session at 9 p.m., it's about climate change adaptation in the smallholder farming sector. This session will start at 9 a.m. Then we have a second session at 2 p.m. tomorrow also. It is about applying analytical and monitoring tools to improve climate change adaptation in the agricultural sector. So also, please join us in these two important sessions tomorrow. Thank you all very much, and bye-bye. Thank you.
Thank you. Bye-bye.